So we're really pleased to have Karsten Borgwardt with us. Karsten is professor of machine learning at TGH Zurich, but also in the Department of Biosystems Engineering, physically located in Basel, so a little bit out of Zurich. Professor Borgwardt is currently coordinating a national scale effort of the personalized Swiss sepsis study that aims to tackle sepsis prediction in the ICU, a topic that is very near and dear to all of our hearts in this community. And it's really comprising basically all university hospitals in Switzerland. He's also coordinating a big training program, the Marie Curie Innovative Training Program on machine learning frontiers and precision medicine. That is pretty big. It's, I think, currently enrolled 14 PhD students spread out over 12 locations in 8 countries. And unfortunately, all of those spots are taken up right now, but they're also doing virtual summer schools on ML in medicine, and you should definitely look for those. Karsten is going to give us a great talk about, as I said, a topic that's near and dear to our hearts, predicting sepsis in the ICU. And it's sort of a go back to basics talk that's going to start with some fundamental questions about how we evaluate the literature and how we compare results and set up or frame the technical problem. And then going to conclude with some pretty interesting results about the generalizability in the sense of external validity of some of the models you can build off of these publicly available data sets. Karsten, take it away, please.
Good afternoon. It's my great pleasure to be here and to present our work on the early recognition of sepsis using machine learning. Why is there a need for biomarkers or predictive systems for sepsis? Why is it so important from a clinical point of view to recognize sepsis early? Well, sepsis is the major cause of death in intensive care units around the world. There are up to 50 million cases per year, and almost every 2.8 seconds, one person dies from sepsis. So sepsis is really a global health crisis. Sepsis, to start with a rather informal definition, is a combination of an infection and subsequent organ damage that occurs in a patient, which may have severe consequences resulting ultimately in the death of a patient. It's not as if there were no cure for sepsis, so antibiotic treatment can often prevent sepsis, but only if sepsis is recognized early and treated promptly. There are many weak indicators, we would call it in machine learning, weak symptoms of sepsis, like slurred speech, shivering, passing no urine all day. But none of them is a highly accurate predictor that someone will develop sepsis soon. So we are still lacking a criterion, a predictive system, a molecular or digital biomarker that will tell us that someone is very likely to develop sepsis. And even if you survive sepsis in the intensive care unit and are discharged from the hospital, there may be long-reaching consequences of having had sepsis, so from difficulty in swallowing to poor memory to anxiety, fatigue, difficulty sleeping, and so on. So all of these various consequences can remain even after you have survived sepsis. Now, to give you now the formal and official international consensus definition of sepsis, sepsis is a life-threatening organ dysfunction caused by a dysregulated host response to infection. And as I said before, it can often be prevented by antibiotic treatment, but bacterial species identification in the blood still takes between 24 and 48 hours. So there's still a long time delay until you can often choose the right antibiotic, and this delay is harmful to the patient. Each hour of delayed effective antibiotic treatment increases the mortality. And therefore, detecting sepsis early to be able to treat it early is of highest clinical interest. And even Niccolo Machiavelli, famous for his work, the Il Principe, described this for another condition, hectic fever, but very accurately it also fits exactly what we want to do in sepsis. So he said that hectic fever at its inception is difficult to recognize but easy to treat. Left unattended, it becomes easy to recognize and difficult to treat. So this statement gives the motivation for our work. We want to recognize sepsis early when it is still easy to treat. We want the machine learning to do this difficult recognition, this difficult early recognition of sepsis. How do we do this? Let me first describe here on a high level the input and the output. So what we use as variables for the prediction are the rich information types about a patient that are being collected, the rich set of variables that's collected about a patient in intensive care units. I'm speaking here of physiological signals that are being measured there constantly, like the body temperature, heart rate, blood pressure, respiratory rate, and many others. Also information about the health state of the patient and the health history of the patient. So these we feed into a machine learning algorithm, and then we try to predict sepsis-related phenotypes like the onset of sepsis, whether there will be a form of septic shock in the patient, a severe form of sepsis, or whether the patient might even die from sepsis. And now in my lab, we have pursued two methodological approaches to this problem. The first one we call association mapping in time series. You can think of this as a form of feature selection in time series. Here we try to find subintervals in these time series that are being recorded that are associated with later on developing sepsis. We use the term association mapping here to draw a connection to the genome-wide association mappings that happen in genetics. So here you can think of this as a time series-wide association mapping. We try to find trajectories, time series motifs that are associated with developing sepsis. This is not the focus of my talk today, but if you're interested in this topic, then I recommend these two publications of ours shown here to you, Bock et al. Bioinformatics 2018 and Gumsch et al. Bioinformatics 2020. We there describe how to efficiently find these time series motifs and how to correct for multiple testing in this challenging feature selection problem. Now, the second approach we take is the more common one in the literature, and that is classification of time series in order to predict sepsis. And this will be, in fact, now the focus of my talk today, this attempt to predict sepsis through time series classification. As I just said, we are not the only ones that are pursuing this approach of predicting sepsis using classification. We did a systematic literature search and found more than 20 papers that propose an approach for doing so. So there's a growing number of such attempts to predict sepsis using classification approaches, but can we even compare these different approaches? And how should one compare them? And are there common insights across these different prediction tools, or are there common challenges and pitfalls that make them non-comparable or even not useful in clinical practice? Well, to answer all of these questions, we very recently published a systematic review on the early prediction of sepsis in the intensive care unit using machine learning in Frontiers in Medicine, first authored by Michael Moore and Bastian Rieck from my lab. Now, our initial search found more than 900 papers that had sepsis and AI or machine learning somewhere in the text, but several steps of quality filtering and reading of the papers then brought this down to 22 studies that really discuss a form of sepsis prediction using machine learning. 21 of these presented a new approach, and one presented a data set for a new challenge regarding this topic. So 21 of these are retrospective studies where you try to predict sepsis using data that has been collected before. And 12 of these use the MIMIC database that is very popular in this community. Various definitions of sepsis are being used. There are various versions of the international consensus definition of sepsis, the latest one being sepsis 3, but 12 of these studies used the predecessor, sepsis 2, and 9 used sepsis 3, and 1 used sepsis labels annotated by clinicians. Now, the challenges that we observed when comparing these different approaches to sepsis prediction was the heterogeneity in the label definition. So you just saw, so some use sepsis 2, some use sepsis 3, one uses expert-driven annotations. But there's even heterogeneity in the label extraction. So even if you settle for one definition like sepsis 3, the way how you implement it may still differ, because that's a very complicated definition that includes a lot of variables. Some of them have to be compared to a base value. And then it's, for example, a challenge how to define this base value, this base line. And then even the same definition may lead to different sets of cases in a study. So we observed in some papers 1 order of magnitude difference in the number of cases when you implement the same definition on the same data set because of implementation details. Reproducibility is a big issue. Often the code for sepsis prediction is not available, and the code for the label extraction, for the endpoint definition, for defining the onset of sepsis is also not available. Another challenge is circularity. You should not use exactly the same observations for defining the onset of sepsis and for predicting the onset of sepsis to avoid circularity. And evaluation is very tricky in this domain, because when you have an onset of sepsis in the cases, in the most common evaluation strategies, you then also have to define a so-called pseudo-onset of sepsis in the controls. How exactly do you do that? Well, turns out this has actually a major impact on the results, how you define this control onset. Let us have a deeper look at these evaluation strategies that are being used in these 21 papers that propose a new approach. So 19 of them use a strategy that we refer to as offline training plus horizon evaluation, and 2 use a strategy that we call online training plus online evaluation. What do we mean by these terms here in this context? So offline and online do not exactly mean match the meaning that is often used in the mainstream machine learning literature here. So there are subtle differences, but these will become clear in a minute. So what do we mean by offline training? So actually the online and the offline training approach are both retrospective. So we look at a data set of cases and controls. And now in the offline training, we have we annotate a time series such that we have a sepsis onset time in that case according to the sepsis 3 definition. And then within this time series, we choose a feature window to represent the case. This is often like even the entire time series, or the entire time series up until the sepsis onset, or the entire time series up until X hours before sepsis onset. But now to compare these windows of a certain length to similar windows in the controls, we have to define a pseudo onset of sepsis in the controls as well. Well, they don't get sepsis, so it's really a pseudo onset. And there are now various ways how you can define this onset. You can pick it randomly across the stay of that control. You can match it to a case such that if sepsis occurs X hours after admission to the ICU in that case, you pick the onset in the matched control to be also X hours after admission of the control to the ICU. And there's the relative onset matching that you say the sepsis onset in the case occurs after 70% of the stay time in the ICU. So we put the sepsis onset into control also at 70% of the length of that stay of this control patient. So 3 different approaches how you can define the pseudo onset, and then define a relative time window relative to that onset that you can compare to the case feature windows. Of course, how you do this affects your outcomes and your results a lot. And then once you have set up this machine learning problem for training in this offline fashion, then what's often being done is a horizon evaluation. So you go back 1 hour, 2 hours, 3 hours, 4 hours from the sepsis onset and the matched pseudo onset in the controls. And you then find out by predicting sepsis or not, whether X hours before sepsis onset, your algorithm is able to accurately predict that sepsis will happen on or not. So this is what we call a horizon evaluation, predicting whether X hours into the future sepsis will occur or not. And now in the online strategy, you don't do a full time series classification, but you rather do 1 prediction per time point in both time series. So this is shown here in this graphic. So these are stays of different lengths. So the cases in the ICU a bit shorter than the control. This may be even unrealistic, but that's the example chosen here. So we make 1 prediction per time point. This is usually hourly for the case. And there is a time point at which the patient develops sepsis. And this time point gets a label of 1, and the neighboring time points, so slightly before and after, also get a label of 1. Like now, it's a matter of definition how big you make this window. So it should be a window within which you are comfortable that the time point here should reflect that the patient is in a state of sepsis. This is what you do on the training data. And then you make a prediction per time point in the case and in the control, and it should predict 0, so no sepsis everywhere but around the sepsis onset in the case. In this manner, with this online prediction, you make hourly predictions, and you avoid to have to define this pseudo onset for the controls. This is a big advantage of the online strategy. Another advantage, this is also shown here on the slide, is that you can deploy this system directly in the clinic. So this is what we want to do in the clinic, doing hourly, doing regular predictions. We don't want to retrospectively pick a time window as we do in the offline strategy. And it's exhaustive in the sense that it really makes for every time point a prediction. But you have to make this label shift decisions, like how big is the time window around the sepsis onset that you deem sepsis representative, to describe it in my own words. Now, in the offline strategy, you often have a clearer sepsis signal because you directly compare these fixed length time windows in cases and controls. You have a notion of earliness in the horizon evaluation because you compare predictions to each other that are being made on patients that are X hours before sepsis onset, or in the controls, X hours before sepsis pseudo onset. And the bottleneck is, however, and this I stressed before, this need to define the exact pseudo onset time for the controls. In fact, 16 out of 19 papers that use this approach of control onset definition do not give details on how it is being done. So that's a big difficulty in comparing different approaches to sepsis prediction. But another big difficulty is that there is a lack of external validation. More than 85% of the studies do not use any external validation data set. So we don't know whether these approaches will really transfer to other ICU data sets in other hospitals or even other countries. The huge bottleneck is the availability of all variables to define sepsis in different data sets. Often these are just not all available, for instance, to compute the sepsis-free label on an hourly basis. And therefore, the generalization abilities of sepsis detection algorithms is at this point very unclear. Recently, there was a paper by Wong et al. Saying that one commercial system did not generalize well when moving from one hospital system to another. And all of this motivated a large study of ours to harmonize the major public ICU datasets and to examine external validation properties of sepsis prediction algorithms there. And this we recently put on arXiv, this paper. It's called Predicting Sepsis in Multi-Site, Multinational Intensive Care Cohorts Using Deep Learning. Now, what we do in this paper is that we harmonize in a big effort all major public ICU datasets into one harmonized dataset. We used 4 of them then for the subsequent machine learning because the Inmori dataset had less variables. The other 4 had a joint set of 63 variables that we could use for sepsis prediction across these different datasets from 3 different countries, so USA, Netherlands, and Switzerland. We use an online evaluation strategy as described before. So we used the sepsis 3 onset to define when sepsis starts, and then we picked a time window that starts 6 hours before sepsis onset and ends 24 hours after sepsis onset. So this is the time window within which we hope that the algorithm will detect a sepsis signal in the patient data. For all other time points, we in the training data set, we label them as 0, including no signal of sepsis. And then we could do what hasn't been done before in the literature. So we tried various prediction algorithms, more on this in a minute. And then we checked how the best of these performs when training on one of these ICU datasets and then moving to another of these ICU datasets. So the results are shown here in this matrix in terms of area under the ROC curve ability to distinguish a sepsis patient from a non-sepsis patient. On the diagonal here, you can see the internal validation. So what is the area under the ROC curve that we obtain when training on AUMC on the Amsterdam dataset and testing, validating also on that dataset. That is 92%. And then the second entry on the diagonal is 83% for the HIRIT dataset from Switzerland, and it's 83% for MIMIC and 80% for EICU. And now the other entries, the off-diagonal entries, tell us how good the prediction works if we train on one data set and predict on another. And interestingly, it works overall extremely well. So we reach, on average, an area under the ROC curve of 76% in this effort to predict sepsis on an unseen, on a new data set. So we show here successful external validation results in this approach here. And particularly interesting is also the last line. This is now another setting in which we don't train on one data set, but we pool all other data sets. So if we try to predict on Amsterdam, we pool all other data sets and build a predictor on each of these other data sets, and then take the maximum of the prediction scores over these 3 or over these usually 3 other data sets, and then predict on Amsterdam. And that works extremely well. This pooled strategy of combining predictors trained on the other data sets here reaches very high levels of area under the ROC curve in external validation. So between 72% on MIMIC to 84% on the Amsterdam data set. So that was very amazing. We even didn't have to pool the training data sets. We only combined the predictions here. And so amazingly, the results were as good or even better than choosing the best single training data set for this task. We compared a number of different classic statistics and machine learning approaches and clinical scores for this task of predicting sepsis, and it turned out that a deep self-attention model outperformed all others. This is shown here as an example on the Amsterdam dataset in internal validation and external validation. And we also examined how early these predictions are, and in internal validation, we see here in this plot, for example, if we want to discover 80% of all sepsis cases, then we have a precision for our model, the attention model, of around 50% 4 hours before sepsis onset. And in the external validation, it's still around 35% for the attention model, 35% precision at 80% recall, an hour before sepsis onset. So we can summarize that we here successfully validated sepsis prediction across hospitals and continents and across data sets. And we are very surprised that combining predictors works empirically at least as well as using the best unknown, in fact, single data set predictor. All of this data and code will be publicly available. Some of it already is. And so we are very happy about this result. A similar success we had in predicting circulatory failure in a paper with the lab of Gunnar Rätsch and Tobias Merz that appeared last year in Nature Medicine, where we could also predict circulatory failure with machine learning techniques. Now, to come to an end, we'll now study this further in a national network in Switzerland, the Personalized Swiss Sepsis Study, and we will also use molecular omics data for sepsis recognition in this context, and we'll create a new ICU data set for which we have already collected 10,000 health records across ICUs in Switzerland. So sepsis is a very exciting problem. Automated diagnosis, biomarker discovery, and biomedical data management, key topics in machine learning, are all present in sepsis prediction. So it's like a very representative topic to work on within machine learning in medicine. What we'll do next is what I just said. We'll harmonize the Swiss ICU electronic health records. We'll integrate omics data into our predictions. We plan to do a clinical validation of our predictions, and it will be interesting to integrate pre-ICU and post data and post-ICU phenotypes into our model. And many of the approaches and insights and problems described here apply to other clinical prediction tasks as well. To conclude, sepsis prediction remains a highly exciting topic in machine learning in medicine. I thank you for your attention, and now I'm happy to further discuss this topic and the general topic of machine learning in medicine with you. Thank you.